We will now study triple integration. Now, as we have seen previously, single integration is done over an interval, and double integration is done over a region in the plane. Triple integration is done over a surface in space. As with double integration, we will begin with the simplest surface, a box. We will then expand this idea to a more general surface. So we define a rectangular box as B is AB cross CD cross EF. So we divide the interval AB into L subintervals, each of length delta x equals B minus A over L. The interval CD into M subintervals, each of length delta y equals D minus D over M. And the interval EF into N subintervals, each of length delta Z equals F minus E over N. Then B is divided into L times M times N sub-boxes, B sub I, J, K. For each I, J, K, consider a sample point, X sub I, J, K star, Y sub I, J, K star, Z sub I, J, K star, in the sub-box B sub I, J, K. We can see that the volume of the box is then delta V equals X times delta Y times delta Z. The hypervolume is then given by f of this sample point times delta V. Now the hypervolume is just the four-dimensional analog of volume, just as volume was the three-dimensional analog of area. The total hypervolume is then approximated by this triple summation. We call this a triple Riemann sum. And just as we did with double integration, we define the triple integral as the total hypervolume, which is found by taking a limit. So the triple integral of a function f of xyz over the rectangular box AB cross CD cross EF is defined as, it's expressed now this way, triple integral over B of f of xyz dv, and it's the limit as the norm approaches 0 of this triple summation. And remember, this norm here, this just represents the maximum of delta x, delta y, and delta z. If this limit exists. So we can now write Fubini's theorem for triple integrals. If f of xyz is continuous on the rectangular box, AB cross CD cross EF, then the triple integral over B of f of xyz dv can be written as a iterated integral, except this time it is a triple iterated integral. So it's the integral AB, integral CD, integral EF, f of xyz dz, dy, dx. Now, the order of integration is changeable, just as it was with double integration. So let's evaluate the triple integral over b of x squared yz dv, where b is this box shown here. So the first thing to do is let's actually go ahead and define b. Right? So it is a set of all points x, y, z such that if we look, x goes from 1 to negative 2, it looks like. Right? So it'll be negative 2 less than or equal to x, less than or equal to 1. Now if we look at y, right, so y here is 0, to 3. And now we need z. So it goes from 1 to 5. So the triple integral over b of x squared y z is equal to the integral from -2 to 1, integral from 0 to 3, integral from 1 to 5 of x squared yz dv. Now, just as with double integration, we can actually write this as a product of three integrals because we can write our function as a product of three functions. One is strictly of x, one strictly of y, and one strictly of z. However, I am going to do it normally one at a time. I should write this as dz, dy, dx, simply because later you have to do it, so it's just better to get used to it. So this will be integral from -2 to 1, integral 0 to 3 of x squared y z squared all over 2. Evaluate from z equals 1 to 5 of then dy dx. So if we evaluate this out, we'll get the integral from -2 to 1, integral from 0 to 3 of 25 halves minus 1 half x squared y. So that is just simply 12 x squared y. So it'll be the integral from -2 to 1 of 6 times x squared times y squared. Y equals 0 to 3. So evaluate this, we get 6 times 9. So we have the integral from -2 to 1 of 54 x squared dx. So this will equal 54 over 3, which is 18, x cubed, x equals -2 to 1, and that will evaluate out to 162. So evaluating a triple iterated integral is exactly the same as evaluating a double iterated integral, except now there's an extra variable that we have to integrate with respect to. So now we can look at triple integration over a general surface. So consider a region W that is enclosed between two surfaces, z1 of xy and z2 of xy, over a domain D in the xy plane, as we can see here. Here's our plane space, sorry, our surface in space. This is one surface, this is another surface up here. And so it can be represented like this here. Now, such a region is called Z simple. Furthermore, this D here is referred to as the projection of W onto the XY plane, as we can see here, right? It's kind of like a shadow. Similar definitions exist for Y simple and X simple regions, right? So this discussion has a natural extension if it's X simple or Y simple. So we now define a new function, just as we did with double integration, f tilde, which will be f of x, y, z whenever x is in W, and 0 whenever x is not in W. Then, if B is a box that encloses W, we can write the triple integral over w of f of xyz dv is equal to the triple integral over the box B of f tilde of xyz dv. And this will now allow us to extend Fubini's theorem. So the triple integral of a continuous function f of xyz over this given region, where d is the projection of w in the xy plane, is the iterated integral, double integral over d of the integral from z1 to z2 of f of xyz dz, and then all dA. We can also apply this if w is x simple or y simple by making the appropriate adjustments. So let's go ahead and evaluate the triple integral over w of 5x minus 3y dv, where w is the tetrahedron bounded by the planes x equals 0, y equals 0, z equals 0, and x plus y plus z is equal to 1. So I'll do my best to sketch this in 3 dimensions. So let's say this here is 1, 0, 0. Let's say this here is 0, 1, 0, and this up here will be 0, 0, 1. Then this right in here is our domain of integration. Now we want to look for the projection on the xy plane. So we draw an xy plane. This would then be 1, 0. This here would be 0, 1. And it is just this triangle. So this is our domain D. Right, whereas this would be our domain W. So this is the projection of W onto the xy plane. Now, this line here is the line x plus y equal to 1. Right, this entire surface here was x plus y plus z is equal to 1. So our domain, this projection here, this D, can be expressed as 0 less than or equal to x less than or equal to 1, and then 0 less than or equal to y less than or equal to 1 minus x. Right, so then W is 0 less than or equal to x less than or equal to 1. It's the same as the projection, except now we have 0 less than or equal to z, which is less than or equal to 1 minus x minus y. So we can now set up our triple integral. So the triple integral over w of 5x minus 3y, and just make sure that was right, yep, is an iterated integral. So we have 0 to 1, then the integral from 0 to 1 minus x, and then 0 to 1 minus x minus y. dz, dy, dx. So if we evaluate it, we'll get integral from 0 to 1, then 0 to 1 minus x of 5x minus 3y all times z, from 0 to 1 minus x minus y, dy, dx. So we get 0 to 1, 0 to 1 minus x of 5x is 3y times that 1 minus x minus y, which, when we simplify it, should give us 5x minus 3y minus 5x squared plus 3xy minus 5xy plus 3y squared dy dx. Now what we can do is group our x terms together, group our y terms together. So we'll have 0 to 1, 0 to 1 minus x. So we'll have this here, 5x minus 5x squared, then plus minus 2xy plus 3y squared. I'm missing a minus 3y, then dy dx. And the advantage to doing it this way is this is now constant with respect to y. So if we now go ahead and evaluate this, we'll have integral from 0 to 1, 5x minus 5x squared all times y. Then we have minus xy squared minus plus y cubed, then minus 3 halves y squared. Y will go from 0 to 1 minus x. So this is the integral from 0 to 1, 5x minus 5x squared times 1 minus x times 1 minus x squared plus 1 minus x cubed minus 3 halves times 1 minus x squared dx. And if you evaluate this, you'll get 1/12. So at this point, I just plugged it into a calculator to evaluate, so I used the computer algebra system. Again, the concern here is being able to set up the triple integral, not actually knowing how to evaluate integrals. That was tested in Calculus 1 and Calculus 2. So now let's go ahead and evaluate the triple integral over w of the square root of x squared plus z squared, where w is the region bounded by the paraboloid, y equals x squared plus z squared, and the plane y equals 4. So here I'm going to try to sketch out the projection. Right, so y equals x squared plus z squared. If you look at the projection, this is the x-axis here, this is the z-axis here, with the plane y equals 4, right? So you can plug in here, you get 4 equals x squared plus z squared. That is going to be a circle of radius 2. On the xz plane. I may have said xy plane earlier, I misspoke there. And of course, this is just the curve. X squared plus z squared is equal to 4. And this in here is our domain D. So we can express d as -2 less than or equal to x less than or equal to 2, and then negative square root of 4 minus x squared less than or equal to z less than or equal to the square root of 4 minus x squared. Now here is definitely beneficial to express d in terms of polar coordinates, right? So when we go to set up our double integral, it will integrate with respect to y, and then we have polar. So if I express this in polar, 0 would be less than or equal to r less than or equal to 2, and then 0 would be less than or equal to theta less than or equal to 2 pi. So a triple integral over w, the square root of x squared plus z squared is the double integral now over d of the integral now of x squared plus z squared to 4 of the square root of x squared plus z squared dy, and then we have dA. So when we go and evaluate this, we'll get the double integral over our domain D of y times the square root of x squared plus z squared, right? And then y, of course, goes from x squared plus z squared to 4. And so we're left with this double integral over D of 4 minus x squared minus z squared times the square root of squared plus z squared dA. We now convert this into polar. So integral from 0 to 2 pi, integral from 0 to 2 of 4 minus r squared times r, then r dr d theta. So 0 to 2 pi, 0 to 2 of 4r squared minus r to the 4th dr d theta. Since there's no thetas involved, I can just write out a 2 pi. So we're then left with integral from 0 to 2 of 4r squared minus r to the 4th dr. So integrating this, we have 2 pi times 4r cubed over 3 minus r to the 5th over 5 from 0 to 2. And when all is said and done, this is 128 pi all over 15. Now, just as we could use double integrals to express an area, we can use triple integrals to express a volume. So the volume of a solid W is given by V equals the triple integral over W of just dV. And again, just as with double integrals, we can express the average value of a three-variate function as a triple integral. So if f of x, y, z is integrable over a solid bounded region W with positive volume V of W, then the average value of the function over W is f bar of W is 1 over the volume of W times the triple integral over W of f of x, y, z. And of course, we just saw that the volume is a triple integral, so we can also write it as a fraction of triple integrals. So that will conclude a look at triple integration. In the next video, we will look at integrating in both cylindrical and spherical. Right? So remember, we could convert a double integral into polar coordinates. Well, we can convert triple integrals into cylindrical coordinates or into spherical coordinates. And In the next video, we will look at